forces conserve energy. So we want to take a big leap and guess what non-conservative forces do?
They don't conserve energy.
Exactly. So another way of looking at a conservative force is that a conservative force will change energy from one type to another. At this point, I've only talked about one type of energy, but non-conservative forces will transfer energy.
Is that why heat energy is wasteful?
Wait, why what?
Heat energy, thermal energy, also known as dissipated energy.
Of why?
Is that why it's wasteful? Because it
It-
transfers heat?
Thermal energy is, heat energy is just basically a form of kinetic energy.
But
It's
it's
energy
not
that's
conservative?
usually considered the energy that's leaving a system.
So it's not conservative because it's dissipated once it leaves.
Well, energy is not conservative or non-conservative, it's the force. And consequently, the work that is conservative or non-conservative.
Okay.
Transfers energy from one object to another. So if we are hopefully accepting of that without evidence, I'm going to then make the claim, so we have work, total work is changing kinetic energy. The non-conservative work is going to be equal to the change in energy. If non-conservative work is being done, the energy will change. So this brings up, what are the two types of energy? Well, let's go ahead. What are the three types of energy?
Static. Oh, wait.
It's not static and kinetic, it's
Could it
kinetic.
possibly be one of the ones that I brought up just now?
No, I don't think so.
3 times.
Chemical,
Oh,
light,
chemical is a specific form of the other
kinetic potential, and
potential. There we go.
Ah.
Potential energy.
what was the third?
We'll get to that. All right. So we have kinetic energy, which is the energy associated with movement. We have potential energy, which is the energy associated with position. So if you think about, we're dealing with classical physics here. All objects have a speed and a location. Position is probably a better word to use there. Position. So this is associated with kinetic energy. And this is associated with potential energy. Now the symbol for potential energy, as you would expect, is a capital U. I suspect it comes from the German. Not 100% sure. At some point, a capital V is used, but that's the difference. Not here. The other thing that all classical physics objects have, they have a speed, they have a position, they have a mass. So there is an energy associated with mass. This is known as rest energy. Now all of you know the formula for rest energy. What is it?
E equals MC squared.
Yep.
Okay, good. That's what
Isn't that light energy? Speed of light?
C is speed of light. The one thing I'm going to do differently here is that I'm a little R for rest energy, and put a little subscript O next to the M.
That's an O.
What? That's an R and a O.
Okay.
It looks like a heart. It did look like a heart. That's what I thought it was.
That's why I tell you what it is, just in case you can't read my handwriting. This is the rest mass. Now, rest mass is the mass an object has when it's at rest relative to the observer. So when you find the mass in lab, by putting it on triple beam balance is sitting there, it is at rest relative to you, that is the rest mass. It turns out that as objects get faster and faster, the mass starts to change. Now, there'll be some people who potentially could watch this video who would disagree with that, and they say it's not the mass that's changing, it's the momentum that's changing. Part of that is generational. So, I never have not run into a situation where assuming it's the mass that changes has changed anything. Good. It's a philosophical difference. So, if I apply a force to an object from mass, so I apply a force to it, it has an acceleration. If I have an object that starts at rest, theoretically I could apply this force to the mass, it would accelerate, and given enough time, I could get to any speed whatsoever. F equals ma, a equals f over m. So in this classical physics, if I had time here and speed, it would be a straight line forever. It turns out that there is a limit to how fast an object can go. If it starts out lower, if it starts out in our everyday experience kind of speeds, it will never get past the speed of light. Speed of light is a maximum value. So that would seem to slap the face of Newton's laws. So the adjustment is the fact that as it gets faster, the mass increases, so the acceleration drops. And so the graph will look more like that.
So, the square root graph.
More asymptotic. There's a square root in there. We'll get to that in 152. Also, as part of this theory, it turns out that the theory is that nothing can pass the speed of light. So theoretically, if there's an object that starts out faster than the speed of light, it will never get below it. The theorists have come up with a particle called the tachyon, which in theory starts out faster than the speed of light and never go below it, but I'm not quite sure how you find it.
Could something theoretically ever be equal to, or would it always be infinitely close?
Anything with mass would just get infinitely close.
Apparently there was a particle called the demon particle, which is massless.
The photons are also massless. There are a number of particles which are massless, which would be going the speed of light. Okay. So we have rest energy here. C is the speed of light, which is about 300 million meters a second.
Like Jesus.
186,000 miles per second.
Wait, okay, I understand that mass has to increase because of like the Newton's law and stuff, but why? How can we prove that the mass is increasing?
I think 152. We will get to it.
Okay, got it.
That there's some funky stuff that happens. Now, as far as 151 is concerned, this is here just for completeness. We will explore this in more detail in the next course. These two are what we care about here. This combination of these two, ignoring this is called mechanical energy.
That's the third?
No, the third is rest energy, but mechanical energy is just a combination of kinetic. If I ask what's the mechanical energy of an object, it's the kinetic energy plus the potential energy. As far as we're concerned, I will probably just say what is the energy. We are ignoring this. So are these two types of energy, and I haven't really defined potential in much detail yet, but we'll get there. So my non-conservative work here is equal to the change in, well, just kinetic plus potential, which is the change in kinetic energy plus the change in potential energy. I know that the change in kinetic energy is just my total work. So this is work non-conservative is equal to my total work plus the change in potential energy. I'm going to rearrange the order of this. I'm going to bring potential energy over to the left-hand side. So I have negative change in potential energy is equal to the total work minus the non-conservative work. Well, if I take the total amount of work and get rid of the non-conservative, what am I left with?
The conservative.
So this would be equal to the conservative work. So I have this equation here, I have this equation here, and I have this equation here. These are the work-energy relationships. Only the first one is called the work-energy theorem, but the three of them are the work-energy relationships.
What is that W, the subscript of that?
Which one are you looking at?
TOT total?
Total.
Is,
I guess I did net up there and total down here. I'm using them interchangeably.
Is the change in E the same as rest energy for work non-confused?
So change in E is the mechanical energy.
Ah.
All right.
What did you call the three equations again?
The work-energy relationships.
Oh.
All right, we're about to enter into the class participation mandatory segment.
Please don't erase that.
If 30 years from now, let's assume I'm still alive.
Good luck.
Yeah, thanks. All I have to do is just maintain my bad diet and couch potato lifestyle, and I'm sure I'll do it.
My grandpa is living proof that that is wrong.
If I ask you, what is the formula for kinetic energy? In unison,
Right,
all of you,
right.
and those on camera, I expect to respond 1/2 mv squared. Don't embellish. Don't go 1/2 times the mass times the speed squared. 1/2 mv squared is the proper response. And I do want that in unison, and I am serious. If I run into you 30 years from now, and I ask you, what's the formula for kinetic energy? I expect you to know 1/2 mv squared. All right, let's give it a shot. In unison.
Okay.
What's the formula for kinetic energy?
1/2 mv squared.
That was not in sync. We're gonna do it one more time. In sync. Here we go. What's the formula for kinetic energy?
1/2 mv squared. Y'all need to speed up.
Yeah, there seems to be a lag back over there. Well, it was almost the Course of Angels. I guess it was Course of Angels in rounds.
You gotta talk too fast.
If I ask you what's the formula for potential energy, the proper response is which one?
Ah, yeah.
You.
That's exactly what I.
What's the formula for potential energy?
Which one?
All right.
Wow, guys, what?
I expect unison
about
for
you?
kinetic energy. The other one, I have less
What about-
stringent
What
requirements.
about you?
Pardon?
You.
That is just the symbol we're
Would
using.
that work?
No.
Okay.
Now, the reason why I say that is that for every conservative force, there is a potential energy formula. So what are the conservative forces? Well, as I said earlier, it's a force that will change energy from one type to another. Doesn't really help a whole lot.
Yeah.
I will give you the list of all the conservative forces we have dealt with so far. There's a formal definition, but this probably is good enough. And done.
Oh, really?
That is the only conservative force we have dealt with so far.
Is that an E?
It's gravitational force. Oh, on subscript, that's a C,
Okay,
conservative.
I can never quite tell.
Now, there are another one that we will deal with this semester called the elastic force. Sometimes I'll refer to it as the ideal elastic force, such as the force from an ideal spring. In 152, electric force, magnetic force, those are also conservative forces. Non-conservative, everything else. So if I have an object here, close enough to the surface of the planet, and it is going to fall from some initial height to some final height. Let's take a look at the third formula we have down there. I know that the conservative work is equal to the negative change in potential energy. This is some mass M. What are all the forces acting on it as it falls?
Gravity.
Gravity.
Force of gravity.
The force of gravity.
Otherwise known as weight. So the force involved is weight. I'm doing a dot product with its displacement. That should be equal to the negative of U final minus U initial. Weight and the displacement are in the same direction, so this will give us a positive dot product. Weight is mg. And my displacement, I know I'm going to get a positive answer. My initial height is bigger than my final height, so this would be hi minus hf.
Gravitational force is just big G, right?
No, gravitational force is either weight or F sub g, which is equal to the negative UF plus UI. Distributing over here, I have mgh initial minus mgh final is equal to negative U final plus U initial.
Right.
Therefore,
Therefore.
what would be a formula for U that would make this a true statement?
Change in U.
If
No,
U equals
right.
change in U?
No.
I want some formula for U that would make this true.
It means.
I'll write it slightly differently, maybe this
Yeah, it's
slightly different view. If I had
Yeah,
UI, instead of UF, negative UF plus UI, I'll do UI minus UF equals MGH I minus MGH F.
In what kind of U are you looking for?
The kind, I'm looking for some value, some formula for U that, where this would make any sense.
But are you looking for initial or final? Or does it
No,
not
in
matter?
general, I'm looking for a formula for U.
I'm a little confused. What exactly does U represent in that problem?
The potential energy.
So
But
then,
U equals MGH.
Yes, if U equals MGH, then my initial U would be MGH initial.
that's not fair.
Come on.
Or,
There we go.
Wouldn't it be change of MGH? Just
Well,
because-
it's a negative change in U and negative change in MGH.
Oh, wait, forget about
What I'm looking for here is, just as Talon said, if U equals, you know, it would be nice if the board didn't pick up when I'm just close to it, not touching it. If U equals MGH, then U initial would be MGH initial. U final would be MGH final, and plug it in, we would get that. All right, here's the tricky question. What is another formula that would also work?
Oh, I know.
Do you?
Wait, just use weight instead.
What?
U equals weight H.
Oh, yeah. Okay.
I know, technically that works.
That would. I was sticking with MG for weight. What would be another formula that would work? I'll tell you, there's a whole lot of formulas that would work. An infinite number of formulas, you might say.
Can you give me a hint?
That was
There are an infinite number of formulas that would work?
No, like, what's another formula? Like, give me a hint. Cause I feel like I know. Yeah?
Is it just on the tip of your mind, but you can't quite remember it, kinda now?
No, it's not a memory thing. It's looking at it and realizing I'm subtracting one thing from another. So it'd be nice if I had something that would just automatically cancel out whenever I did the subtraction.
Cancel out the weight.
No,
Or
no.
MG.
My reading skills are off this morning. What's up?
What if?
I will hope that you accept that. I will offer it without proof.
Four,
I don't look for it. Maybe if I put a 5 there, what would I put over here?
5.
So if I start out with some basic here, what could I do to make sure that it's still equal?